Alright, calculating relative molecular masses. Relative molecular masses को कैलकुलेट करने का सबसे एक्यूरेट मेथड तो मास स्पेक्ट्रोमीटर ही है, जो हम चैप्टर 3 में कवर कर चुके हैं। बट हमारे पास एक और लेस एक्यूरेट मेथड होता है जो कि स्कूल लैब के लिए बहुत अच्छा होता है, हम उसे यूज करते हैं। वो यूजली मास ऑफ गैस के लिए होता है। हम इसके लिए बड़ा फ्लास्क यूज करते हैं और जनरल गैस इक्वेशन यूज करते हैं। जनरल गैस इक्वेशन को कोई यूज करना हो तो हमारे लिए जो है वो हम जनरल गैस इक्वेशन ही यूज करेंगे, और उस इक्वेशन के अंदर हम जो मोल्स का फॉर्मूला होता है, मोल इज इक्वल टू मास ओवर मोलर मास, उसे रिप्लेस कर देंगे। वे करना गैसेस तो एक डिफिकल्ट प्रोसेस है क्योंकि ये बहुत लाइट होती हैं और आपको बायनेंसी ऑफ एयर भी कंसिडर करनी पड़ती है, लेकिन ये मेथड फिर भी काफी रीजनेबल रिजल्ट्स देता है। हम इस मेथड से कुछ वोलेटाइल लिक्विड्स के मैसेज भी यूज कर सकते हैं। स्टडी वोलेटाइल लिक्विड को इंजेक्ट कर दें गैस सिरिंज में, प्लेस कर दें गैस ओवन में, जब लिक्विड वेपोराइज कर जाए और उसके वॉल्यूम वेपर्स का जो है वो रिकॉर्ड कर लें। मींस हम वोलेटाइल लिक्विड को भी इसी तरह से कर सकते हैं कि वो इजीली गैस में कन्वर्ट हो जाता है, तो हमारा पर्पस उससे पूरा हो जाता है। आर वी सपोज टू डू इट? उसके लिए उसने पहले एक वर्क एग्जांपल दी है ताकि आपको पता चल जाए कैलकुलेशन कैसे होनी है। बाद में हम उसका प्रैक्टिकल भी स्टडी कर देंगे। So let's say a flask of volume 2 liters or 2 decimeter cube was found to contain 5.28 grams of gas. प्रेशर जो है वो उस फ्लास्क में 200 किलो पास्कल है और टेम्परेचर 20 डिग्री सेंटीग्रेड है। रिलेटिव मॉलिक्यूलर मास ऑफ गैस फाइंड आउट करना है। आर की वैल्यू दी हुई है, ठीक है। सबसे पहले तो ये कि आप प्रेशर को, टेम्परेचर को, वॉल्यूम को उनके करेक्ट यूनिट्स में कर लें। रिमेंबर, हम प्रेशर को पास्कल में करते हैं, तो हम वॉल्यूम को मीटर क्यूब में करते हैं, ठीक है। So decimeter cube has been changed converted into meter cube, degree centigrade to absolute temperature Kelvin, and kilopascal into Pascal. Now, we need to go with the general gas equation, which is this. The thing I was talking about in the previous paragraph was to use this equation, but at the same time, use this one in conjunction as well. Now, this equation is number of moles is equal to mass over molar mass. Now, we can simply replace this with the n given in the equation. So this equation becomes PV m over mr into RT. Rearrange the equation so that you can get mr. So this is m small m mass, of course, r into t over p into v, which is pretty simple. If we have these values, we can use them to get the mass. Now, since starting off with this question, you are given with volume, you are given with temperature, you're given with masses, you're given with temperature and pressure, the things that you require. So actually, you have all five pieces of information to get the sixth one, mr, from this equation. So it's pretty easy. आपके पास mass भी होता है, R भी होता है, T भी होता है, pressure भी होता है, volume भी होता है. If you're doing all of this in school lab, ठीक है, तो आपके पास बाकायदा एक वॉल्यूम की फ्लास्क होगी जो जिसको हम फिल अप करेंगे। हम उसके प्रेशर भी नोट डाउन करेंगे, हम उसका टेम्परेचर भी नोट डाउन करेंगे और हम उसके masses भी कैलकुलेट करेंगे। And these four things are easier to perform at school lab if you're not going with very high pressures and not going with very sophisticated equipment. Instead, simple accurate measurements can get you your answer. Now, this seems to be 32 gram per mole, which brings us to a point where we may conclude that this might be oxygen gas, right? So if you go with this kind of calculation, it should be pretty easy determining the whole thing. Let's go with the practical activity so that you can connect the dots and understand the whole thing. So as you can see, we have a syringe-based big oven. This oven is connected to a self-sealing rubber cap. Now we have a hypodermic syringe, a normal syringe that is connected to this one. And in this syringe, we can put up a volatile liquid or gas. Both of them can be taken. Now we have gas syringe over here, we have the thermometer, and we have the light bulb. Now we use the light bulb in order to keep the temperature as the way we want it to. Now, what are the steps? Put the gas syringe in the syringe oven and leave until the temperature is in constant. Record the volume of air in the gas syringe since this is supposed to contain air. Fill a hypodermic syringe with the volatile liquid and find its total mass. Inject a little of the liquid into the gas syringe and find the total mass of the hypodermic syringe again. Allow the liquid to vaporize in the gas syringe. Now, record the final mass of vapor plus the air in the gas syringe. Record the atmospheric pressure, temperature, and pressure. The calculation is carried out in the same way as example 3. So how do you work with it? The volume of vapor produced is final gas syringe volume minus initial gas syringe volume. Then the mass used in calculation is initial mass of hypodermic syringe plus liquid, subtracting final mass of hypodermic syringe plus liquid. So if you subtract both of these, you would easily be able to get your answer. Make sense? This will get you the mass value. This will get you this value. This would get you T and P. Since all you needed was this, all right? So there you go. You have all of these. Since this is a constant quantity, 8.31 joules per Kelvin per mole, so you are simply going to put the value for the rest of these. You have calculated them. There you go. You can easily calculate your MR. From MR, you may jump to conclusions which gas it is. Since there are very less gases on the periodic table, it should be easy if you're going with a simple elemental case. In case of molecular case, you can make a few guesses. All right. A few questions like these should really help you out. Question number 6, part A and B, should be easier for you to solve. And following with question number 7 and 8, it should give you the idea. Solving these questions before you start off with past paper questions is really going to help you working with this question. So, any questions? No questions, then let's move on to the liquid state. The behavior of liquids. Now, when we heat a solid, the energy is transferred to solid, make the particle vibrate more vigorously. The forces of attraction weaken. The solid changes to a liquid, and this happens at its melting point, after which the arrangement and the packing of the solid changes, and we get the liquid. The melting point of the solid is the temperature at which it changes to a liquid at 1 atmospheric pressure. Here we are specifying 1 atmospheric pressure since around the world this is the standard pressure. But of course, at higher altitude, since this value changes, that's why the melting or boiling point when values may change too. All right. I hope you know that already from O levels. Do you?
Yes, sir.
Good. We call this change of state melting. For any compounds, we need a high temperature to melt the substance because from the previous chapter, we know that ionic bonding is very strong and we need to break those bonds in order to overcome those and then convert the lattice into such a structure that the ions can freely flow, hence the liquid state. For molecular solids, we need a much lower temperature. We just need to overcome the weak intermolecular forces between the particles. We do not try to break their covalent bonds. Remember this stuff as this is a very important point and is usually manipulated a lot in MCQ paper, paper 1. The particles in liquids are still close to one another, but they have enough kinetic energy to keep sliding past each other in a fairly random way, hence the flow of the liquid. They do not move freely as gas particles do. For brief periods, the particles in liquids are arranged in a slightly ordered way, but this order is always being broken when the particle gains kinetic energy from neighboring particles through collisions. Remember, this line can be completed if you use the term through collisions. All right. So yeah, particles collide with one another and particles keep exchanging their energy too, and hence the order is kept breaking up. When we cool a liquid, the particles lose kinetic energy, so they don't move around so readily. They experience the increasing forces of attraction since forces of attraction begin to increase more and more. And with higher forces of attraction, the particles can be attracted to kept closer. So they stop sliding past each other. When the temperature is sufficiently low, the liquid solidifies, and we call this change of state as freezing. So he has completely explained melting, and from melting, he has completely explained freezing, along with explaining the kinetic theory for liquids. I hope this makes a lot of sense. Most of these stuff already did back from O levels, but since a few more things have been studied afterwards, so I think this should be easy for you. Moving on, vaporization and vapor pressure. When we heat a liquid, the energy transferred to the liquid makes the particle move faster. Now, the forces of attraction between the particles weaken. The particles with most energy are the first to escape from the forces holding them together in a liquid. Now, this brings me to a point that I should explain to you how this works. Now, in the case of liquid, though this is more correct for gases, but let me explain. Let's consider we have a beaker, and in that beaker, we have a liquid. And in those liquids, the particles are moving, sliding fast over one another. Let me tell you, even in a liquid, the particle, their motion or the speed is divided into three different categories: the fast moving particles, the moderately moving particles, and the slow moving particles. All right. This bifurcation of movement of particles or speed of particles is true for liquid, but it is much more true for a gas. All right. Since our gas particles can easily be divided into these three categories. When we talk about this kind of categories, why am I discussing the categories? I am discussing the categories because these categories are very important both for liquid state and for gaseous state. How? Let's start with the liquid state first. Starting with the liquid state, this point talks about with most energy particles, since they are the first one to escape from the forces holding together in the liquid as soon as these particles reach the surface. And this is known as evaporation. Evaporation usually happens to particles that reach the surface and fall under this category in specific. Since they're moving towards the surface, if they reach the surface, they will leave the surface as a vapor. The process is known as evaporation, and it may occur at any temperature below the boiling point. I hope when I categorize these speeds for different particles, and when I explain it that way, you would understand instantly what evaporation is all about. And the only condition of evaporation that we discuss as a part of its definition, that a temperature below the boiling point. Now, the forces weaken enough for all the particles to become completely free from one another if we're going to keep it heating, right? Since we were talking about this phenomenon. So, if we keep on with this phenomenon, we will be able to convert slow particles into moderate ones, moderate into fast ones, and the fast one into super fast ones. Who has the most chances of leaving this surface as a vapor? What do we say? We say the liquid boils, and this happens at the boiling point. Since at the boiling point, we are able to pick up all the categories and surpass them from the fast category, the minimums of fast category. Does this make sense to you? If not, please ask. Specifically, the last one, the last point. All right. If it does, moving on, the change from liquid state to gaseous state is called vaporization. The energy required to change 1 mole of a liquid to 1 mole of a gas is called as enthalpy change of vaporization. Now, this would make much more sense. You might be thinking, why do we need the word vaporization as soon as I get to this line? The change of liquid state to gaseous state, if that occurs at a boiling point, we call that boiling. So why do we need another word? We need another word because we need to connect it to the energy change and with the specifics of 1 mole of a liquid and 1 mole of a gas so that we can give it a name on the enthalpy change scale. Now it should make more sense to you. Why do we use the word vaporization instead of boiling? Now, moving on, when we cool a vapor, now we're going to study the vice versa. When we're going to cool a vapor, and I'm going to just erase some of it, and I won't erase all of it since I would require that diagram on top. So let's move a little bit. When we cool a vapor, the particles lose kinetic energy, so the molecules move around less quickly. They experience increasing force of attractions, just like they did the previous time when we were discussing freezing. It's pretty much similar, but there are some rules which we cannot break when we talk about freezing in comparison to condensation. Now they move more slowly and become closer together when the temperature is sufficiently low. The gas liquefies. We call this change of state as condensation. Make sense?
Yes, sir.
Okay.
Yes.
The changes in state are reversible. Water can be boiled to form steam, and steam can be condensed to form liquid water. These changes involve opposite energy transfers. For example, energy has to be transferred to water to boil it to form steam, but the steam condenses to form and gives away energy to be transferred from steam to water. If we put some water in an open beaker, it evaporates until none is left. But what happens when we allow the water to evaporate in a closed container? Let's discuss the closed container. And these diagrams serve the purpose for closed container. Take a look. When we put it in a closed container, the evaporation starts even in the closed container. The particles that are present on the surface face less forces of attractions as compared to anyone in the bottom. For example, take a look at this particle that I've colored blue. This one is attracted by this particle, this one, this one, this one, this one, and it cannot leave the system since it's surrounded by particles. Talk about this particle, this that I colored blue. This is only attracted by these three particles. Since there are no attractive forces from top, it may leave the surface and become a vapor, like this one did. Now, some of the vapors may come back to the surface and they will have to face the attractive forces and they might stay with the surface. This is known as condensation. Now, evaporation and condensation in a closed container works as reversible reactions, and water molecules move from liquid to vapor. As more molecules move from liquid to vapor, some begin to move back to the liquid. Then an equilibrium is reached with molecules going from liquid to vapor at the same rate as from vapor to liquid. So we say, for the sake of understanding, we say, let's say if 10 molecules are being converted from liquid to vapor, 10 vapors are converted back into liquid state at the same time, hence the same rate, hence the term equilibrium. So explaining this, and I'm going to erase just some of it, not all of it. All right. So explaining this, we come to its last paragraph. At first, water molecules escape from the surface of the liquid to become vapor. As more vapor escape, the molecules in the vapor becomes closer together. Eventually, the molecules with low kinetic energy will not be able to overcome the attractive forces of neighboring molecules. The vapor begins to condense. So some water molecules return to liquid. Eventually, water molecules return to liquid at the same rate as water molecules escape the vapor. The position of equilibrium is reached. So at equilibrium, the concentration of water molecules in the vapor remains constant. So water molecules in the liquid and water molecules in the vapor, there should be equal movement of both sides to one another. Understandable?
Yes,
All
sir.
right.
Yes.
Give me a minute and I'll be back. So in this situation, the pressure exerted by vapor in the equilibrium with its liquid is called is its vapor pressure. In this specific case, we call the pressure exerted by these vapors as vapor pressure. The vapor pressure is caused by the gas particles since they hit the wall of the container, just like the common air particles do too. Vapor pressure will increase when the temperature increases because of two reasons. The gas particles will have more kinetic energy, so the average kinetic energy increases as the temperature increases. When the gas particles move faster, they are able to overcome intermolecular forces of attraction more easily, and some more molecules would be able to evaporate and will be able to convert into vapors, and will also contribute towards vapor pressure. So increasing the temperature will increase the vapor pressure too. This also is taken as questions in MCQ paper. The boiling point of liquid is the temperature at which it changes to gas at 1 atmosphere or this many pascals pressure. A more exact definition is a temperature at which the vapor pressure is equal to the atmospheric pressure. So I would suggest go with a more exact definition instead of writing this one at all. So it's a temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. Now, this was a part of IGCSE. Sometimes teachers explain this definition to the students, sometimes they don't. So let me go back a little. Let's explain this from this diagram. Let's say I start heating these, all right? When I heating these, there would come a temperature when the pressure of these vapors colliding the wall would be equal to the pressure of the atmosphere, means air molecules colliding with the wall of the container from outside. When these both pressure becomes equal, the vapor pressure over here and the atmospheric pressure over here, when they become equal, that temperature is known as boiling point. All right. This is the more exact definition of boiling point. So a thing boils when the vapor pressure inside this whole closed container system becomes equal to the atmospheric pressure. Does this make sense to you?
Yes, sir.
Now, previously I was talking about altitude. Since at a higher altitude, at mountains or mountainous areas, we have less pressure. I hope you understand that at ocean level, the pressure is considered to be at 1 atm, which is our actual pressure, ground pressure. As we go high, the pressure becomes less. As we go down, the pressure is increased, it becomes more, right? So when we go high, since there is less atmospheric pressure present, we need less vapor pressure and we need less amount of heat or less temperature in degree centigrade or in other units to go with in order to boil material. Let's say if we talk about boiling point of water, right? So if we talk about boiling point of pure water, then that is 100 degrees centigrade at 1 atmospheric pressure or the pressure at ocean level, right? This may be different from mountainous areas. Let me tell you the tip of the Mount Everest, which is the highest portion on this planet, is 69 degrees centigrade for the boiling point of water. And if we go deeper into the ocean, after every few hundred feet, the temperature becomes higher and higher. This 100 can be converted into 120 or 140 as depending upon the depth you're going to get to. I hope now this portion from IGCSE and this explanation would be much more understandable for you. I don't know whether
Yes,
your previous teacher has covered it or not. In case of Laiba, I'm the previous teacher. In case of Ali, I don't know the previous teacher properly covered it or not. Did he?
no, it didn't.
Okay. Well, I used to teach these even back at IGCSE, since this is not a part of our O levels, but this definitely is a part of IGCSE, right? Okay, so let's erase these two. And keep this diagram just to be on the safe side. We don't need the diagram. So I'm going to erase off all of it. Okay, moving on. Solid state. Now, in case of solid states, many ionic, metallic, and covalent compounds are crystalline. The regular structure of crystals is due to the regular packing, a more arranged, a more network, proper packing within the crystal. We call this regularly repeating arrangement of ions, atoms, or molecules as a crystal lattice. Now, I hope you remember back from IGCSE, a lattice was defined as a three-dimensional, microscopic, something that you may not be able to see with your own eyes, regular, repeating arrangement, and we use the word networked arrangement back in IGCSE's book as the complete definition of this crystal lattice. They are supposed to be three-dimensional, they are supposed to be microscopic, they are supposed to be regular, they are supposed to be repetitive, and they are supposed to be networked with one another in terms of forces of attraction or repulsion. And then that arrangement of may that be ions or atoms or molecules is known as a crystal lattice. Now, since they belong to many different they belong to many different states, since they can be ionic, they can be metallic, they can be covalent. Let's start with ionic lattices first. Now, in case of ionic lattices have three-dimensional arrangements, and they are alternating positive and negative ions. With ionic lattices, sometimes are also known as giant ionic structures. The type of lattice formed depends on the relative sizes of ions present. The ionic lattices for sodium chloride and magnesium oxide are cubic. We have discussed that, not exactly the cubic shape, but the rest of it back in IGCSE. In sodium chloride, each sodium atom is surrounded by 6 oppositely charged chloride ions. Now, do you understand this line, Ali? Since I've already taught this to Laiba, so I would like to refer to you. If you don't understand this line, I would explain it more. Otherwise, we're going to just move ahead.
Yes, sir.
You understand this line when we say in sodium chloride, each sodium ion is surrounded by 6 oppositely charged chloride ions. So which 6 directions are we talking about? Do you understand this? Should I explain it, or should I just move ahead without explaining?
Yeah, can you just explain it once?
Yeah, sure, sure. We're talking about this kind of network structure. Maybe you might be seeing that every Cl is surrounded by this, and this, but that is not an exact representation, since it's a two-dimensional representation. Now, I hope you understand from mathematics that we draw a graph based on two axes, x and y. But if I complete this graph, I would also draw x dash and negative x, or negative y or y dash. Now, this is a two-dimensional graph. As soon as we go with a third dimension, we add a z and a z dash or z negative to it too, right? This means this z is coming out of it towards me or towards you, and negative z would be away from you. This is the third dimension. Now, consider the sodium ion to be present in the exact center over here. So every Cl negative would be an ion that is covering the extremmost space on these 6 portions. So what am I trying to say? Imagine you yourself are the Na positive ion. Then there would be a Cl negative ion above you, a Cl negative ion below you, a Cl negative ion in front of you, a Cl negative ion at the back of you, and a Cl negative ion towards the right of you, and a Cl negative ion towards the left of you. I hope from you that you understand that we are covering all 3 dimensions, meaning all 6 points where an Na positive ion can be surrounded by a Cl negative ion. Makes much more sense, right?
Yes, sir.
Good. The chloride ions are much larger than the sodium ion. We know this from chapter 2 and chapter 3, that positive ions are smaller than their parent atoms, and negative ions are actually larger than their parent atoms. So, of course, the chloride ions will have a larger structure, and a positive or sodium ion will have a smaller structure. So, the sodium ions fit into the spaces between the chloride ions, right in between those spaces, as close as they are possible to them. So, we have an extremely tightly packed structure. And this tightly packed structure not just explains its packing, it also explains its arrangement. It's also explained its density, hence solid at room temperature. All ionic lattices are solid at room temperature. Right? So
Yes.
the arrangement of ions in sodium chloride is part of the diagram, the actual packing of the ions in part A in an exploded view, so you can understand or see the arrangement of ions clearly, though this kind of space is not present in between them, hence the term exploded view. Moving on, magnesium oxide has the same lattice structure as sodium chloride. Magnesium ions replace sodium ions and the oxide ion replace the chloride ions. The properties of ionic compounds reflect their structure as well as their bonding. They are hard. They're so tightly packed, of course, they are supposed to be hard. It takes a lot of energy to scratch the surface because of the strong attractive forces keeping the ions together. In order to scratch the surface, you need to peel off some of the ions off of its surface, which you might not be able to do since it requires a lot of energy. They're brittle. Brittle means whenever we try to shape them, they break instead of getting their shape changed. When we're calling something brittle, let me tell you, it's not malleable, it's not ductile, you cannot stretch it, you cannot hammer it, instead it would break. So ionic crystals split apart when hit in the same direction as the layer of the ions. The layer of the ions may be displaced by the force of the blow so that ions with the same charge may come together. The repulsive forces between thousands of ions in the layer, all with the same charge, causes the crystal to split along these cleavage planes. Cleavage are the corners or the boundaries that we can draw. Remember, if you'd like to tear off a piece of paper off of your copy, what do? You fold that piece of paper and then you draw a cleavage with your fingernails, and at that cleavage, you can easily tear apart the piece of paper. That line that we draw with our fingernails is known as cleavage. And the same cleavage happens to be in between these layers. How? When we apply a force on these layers, we push the layers so much so that a Cl negative comes in front of a Cl negative and an Na positive comes in front of an Na positive. So all the same charges would come in front of each other. Since there would be thousands of ions repelling one another, this entire layer would break off. So they are brittle. As soon as we try to hit them, they break apart exactly according to their cleavage planes. And every layer acts as a cleavage plane since a layer opposing another layer with similar charges will create hundreds and thousands of repulsions of the similarly charged ions at the same time. Those repulsive forces causes it to break. You will understand the brittlity and also the cleavage planes. If that's clear, we can move forward. Good. Now, they have high melting points and high boiling points. This is because the forces of attraction are large and they are present in large numbers too. Oppositely charged ion acts in all directions and bonds them strongly together. Previously, when we don't explain the six-part rule of an Na positive surrounded by a Cl negative, the students usually tend to assume that one Na positive would have attractive forces with one Cl negative ion. But as soon as we explain this whole thing, they understand that the forces of attraction for every ion is 6 to 1. And since they can be Avogadro's number of ions, Avogadro's number of positive ions and negative ions in simply 58.5 grams of NaCl. Imagine you need to multiply Avogadro's number with 6 for every positive ion and Avogadro's number with 6 with every negative ion to understand all of the forces separately. Combining the forces, you do not need to multiply both of them with 6, but even then it would be a big number. Since the number would be something 10 raised to power 29 or so, which is a big number when we are calculating attractive forces. With this kind of attractive forces, and you need to break all of them down, of course, you're going to wind up with high melting points and high boiling points. For example, if we talk about NaCl alone, the melting point is around 801 degrees centigrade, and the boiling point is somewhere around 1465. I'm not sure about this value. I'm a little unsure. It may be 1465 or maybe 1765. I'm a little unsure, but this I'm sure about. So this is a pretty high melting point when it comes to that. And the sole reason is this one. Sorry, we have the melting points. No, we don't have the boiling point. Now the melting point with one positive and one negative charge is 801, but the same with two positive and two negative is 2852. Imagine if we're dealing with something like ALN with 3 positive and 3 negative. How strong would that be? So, greater the electrostatic forces between doubly positive and doubly negative ions than the singly positive or singly negative ions of the same size. Which also brings us to a point that if we are comparing NaCl with MgO with ALN, every time you're going for a higher set of charges, you'll have higher melting and boiling points in between the ionic compounds. Well, most of the ionic compounds are soluble in water because they can form ion dipole bonds. I've already explained that. Though this portion will be explained in A2, but some of the explanation that can help you with AS has already been explained in the previous chapter. Now, they only conduct electricity when they're molten or in solution. We've already discussed that in 4.9. If the ions are free to move, only then they can conduct electricity. Otherwise, they won't be able to conduct it. And ions are free to move in molten or solution form. The ions are fixed at their positions in solid form. I hope you don't have any questions from this part. So let's move onward. Now, metallic lattices. Remember that metal conduct electricity when solid or liquid due to mobile delocalized electrons. But ionic joint structures only conduct when liquid, means molten, or when they're in aqueous solution due to mobile ions. So the conductivity is because of two different kinds of species or particles. So you cannot combine them on the basis of their conductivity. In chapter 4, we learned that metallic lattice consists of ions surrounded by a sea of electrons. The ions are often packed in hexagonal layers or cubic arrangement. Lattice of copper ions arranged in a layer. When a force is applied, the layers can slide over one another. But in a metallic bond, the attractive forces between the metal ions and delocalized electrons act in all directions. So when the layers slide, new metallic bonds are easily reformed between ions in the new metallic positions and the delocalized electrons. So you don't have a huge number of repulsive forces coming into play and breaking the whole thing apart. That's why the malleability and the ductility. He has tried to explain the first possible question that may come in a student's mind, that what if we apply forces over here on the cleavage plane of metals, why do they not break? Instead, we can make sheets out of them when we hammer them, or we can make wires out of them when we stretch them or pull them. So the high tensile strength and hardness of most metals is also due to strong attractive forces between the metal ions and the delocalized electron. Since they can easily be reformed, all of these attractive forces, even when the layers slide and keep on sliding after every hammer strike. So what you can use the malleability to a very good point, to a very good level. So much so, we can convert a piece of pure gold of matchbox size by simple hammering into a sheet that can cover even the largest football stadium on the planet by simple hammering. This gives you the idea of malleability, how much they're malleable, right? Because of their malleability and because the layers can slide over one another and reform a new lattice in new positions, we do use metals as their alloys. Now, in case of alloys, what we are trying to do is to mix two metals and use them for a specific property that can be exploited for a specific alloy. Now, alloy is a mixture of two or more metals, or maybe a metal with a non-metal. The metal added to create the alloy becomes the part of the crystal lattice of the other metal. For example, brass is an alloy of copper, which is 75%, with zinc only 30%. Now, it is stronger than copper, but still malleable a little bit. For these reasons, it is used for musical instruments, ornaments, or household instruments such as door handles. So, why is brass stronger than copper? Zinc ions are larger than copper ions. The presence of differently sized ions makes the arrangement of lattice less regular, as shown in this bottom diagram, since you can easily spot the copper ions as well as the zinc ions, right? So the airs cannot slide very easily. This doesn't mean the layers do not slide at all, but not as easy. So what are you getting? By sacrificing, understand this point uh, in a good way so that even if this point is exploited in MCQs, you understand it. You sacrifice a little bit of malleability. What do you get? A more harder, stronger structure. So in alloys, what are we trying to do? We are trying to mix two different kinds of particles in a layer. We sacrifice one, two, or more of the properties to get one, two, or more of the new properties. For example, let's take another example since right beneath this, we have another example. Pure aluminum is softer than many metals. It is ductile, has a high electrical and thermal conductivity. Now, because of its low strength, pure aluminum is of little use in engineering. But its strength can be increased by adding other elements. We may add copper, we may add magnesium, silicon, manganese, the list goes on. Many alloys of aluminum are lightweight, strong, resistant to corrosion. These are used for the bodies of aircraft, for cylinder blocks of car engines, bicycle frames, all situations where low density can be combined with strength and corrosion resistance is important. Now, for bodies of aircraft, you need a low density. The lower weight of the aircraft, faster the speed of aircraft, a higher altitude it can get to, and better efficiency it can perform at. But at the same time, we need strength. Since it's going to glide through the gusts of air, wind, and even clouds when it is high up in the air. And we also need corrosion resistance since over there we'll have all the moisture in the air which may corrode the other materials, but not aluminum or its alloys. So all of these properties are very important just for the bodies of aircraft and for blocks of car engines and bicycle frames. We have the similar situations, but not the clouds and airs, right? So bronze is an alloy of copper and tin. A 33-meter high bronze statue was built near the harbor in Rhodes, Greece, over 2,000 years ago. The statue fell down after an earthquake and was eventually bought by a Syrian merchant. The bronze was recycled to make useful implements. See, even after 2,000 years, we were able to recycle the materials and build something new out of it, which is a pretty important property when it comes to metals. Let's come to simple molecular lattices. Now, simple molecular lattices are simpler, easier structures to study. If you go back to IGCSE, you'll hardly find 4 to 5 lines about them. And we have something similar over here. Simpler molecular structures are so simple to study that you won't find a lot of data about them. This reflects the regular packing of molecules in a lattice structure. For example, for iodine, we have the iodine molecules made from a single bond between an iodine-iodine atom. Ice also forms a crystalline structure. Ice and water have peculiar properties because of ice having hydrogen bonding in its crystalline structure, which we studied in the previous chapter. The distance between the nuclei of neighboring iodine molecules in this is greater than the distance between the nuclei within the iodine molecule. Now, this seems as a little bit surprising. Let me tell you, these are London dispersion forces, all right, temporary ID forces. This is because the forces between the molecules are weak intermolecular forces, whereas the forces between the atoms within the molecules are strong covalent bonds. Very little energy is needed to overcome the weak intermolecular forces between the molecules, so the lattice is easily broken down when iodine crystals are heated, so iodine has a very low melting point, right? Now, when I use these words, you may need to understand that we change its state. Sometimes the students come to argue that why are we using the term melting point if iodine does not melt and simply sublimes into a gas? We sometimes say the word to give the expression to the student of change of state. We're not exactly saying that it is going into liquid state, but we're trying to implement that the solid state can be changed with a little bit of heat. And what's true is that we're not breaking down the covalent bonds, we're only trying to break the or overcome the weak intermolecular forces, which we are very successful even at low temperatures. So this is not about the melting exactly or the sublimation. This is not that kind of discussion. The point they're trying to make over here is to break the weak intermolecular forces between these molecules, overcome them, and change the state. I hope my explanation makes sense, right?
Yes, sir.
Now, they may discuss any set of properties with one another. Now, they are discussing metallic bonding with simple molecular structures in just a single table. They may include or throw in an ionic compound or a joint molecular structure as well. So it's entirely up to them what kind of table they are going to come up with. And that table might end up with some information that you haven't studied much about. Don't worry. There would always be hints between these values which would give you an idea of how you can work out this table compared to the values which are different from one another. All right. Would you be able to work this kind of question out? If not, let me know and I'll help you with it. Getting to giant molecular structures. Now, this one is gonna take a little bit of time. So I think let's put it for another day.